Let's examine the quadratic equation x squared minus 4x plus 8 equals 0. This equation will have complex solutions, which we'll discover as we work through it. To solve this equation systematically, we need to identify its components. First, let's recall the standard form of a quadratic equation, ax squared plus bx plus c equals 0, where a, b, and c are constants. By comparing our specific equation to the standard form, we can identify each coefficient, which will be crucial for applying the quadratic formula later. In our equation, the coefficient of x squared is 1, because the term is simply written as x squared with no number in front. When no coefficient is written, it's understood to be 1. The coefficient of x is negative 4. The negative sign indicates that this term is being subtracted, which will affect how we use the quadratic formula. And the constant term is positive 8. This is our c value, which appears without any variable attached to it. Let's identify these coefficients explicitly so we can use them to solve our equation. The coefficient a equals 1. In many quadratic equations, a is often 1, which simplifies our calculations, but the formula works for any non-zero value of a. The coefficient b equals negative 4. The sign of b will be important when we apply the quadratic formula, as it will affect the direction of our complex solutions. And the constant c equals 8. The fact that c is positive and relatively large, compared to b squared, will lead us to complex solutions, as we'll see when we calculate the discriminant. With these coefficients identified, we're ready to apply the quadratic formula. Since b squared, which is 16, will be less than 4 times a times c, which is 32, we expect to find that this particular equation has complex solutions rather than real ones. Having identified the coefficients a equals 1, b equals negative 4, and c equals 8, we're ready to solve this quadratic equation and explore its complex solutions in the complex number plane. Let's explore how to solve quadratic equations using the quadratic formula, which gives us a direct way to find solutions without factoring. This is the standard form of a quadratic equation, where a, b, and c are constants with a not equal to 0. To solve for the values of x that satisfy this equation, we use the quadratic formula. This formula gives us the solution for x in terms of the coefficients a, b, and c. The plus-minus symbol indicates that we'll typically get two different solutions from this formula, one when we add the square root term, and another when we subtract it. Notice how the coefficients from our standard form appear in the quadratic formula. The a appears in the denominator as 2a and also in the term 4ac under the square root. The b appears as negative b in the numerator and as b squared under the square root, and c appears only under the square root as part of 4ac. The expression under the square root b squared minus 4ac is called the discriminant. It plays a crucial role in determining not just how many solutions we'll have, but what type of numbers those solutions will be. The discriminant is like a detective that tells us about the solutions before we even compute them fully. Let's look at how its value affects the nature of our solutions. When the discriminant is positive, that is, when b squared is greater than 4ac, the quadratic equation has two distinct real solutions. This means our solutions will be two different points on the number line. For example, if we had x squared minus 6x plus 8 equals 0, the discriminant would be 36 minus 32, which equals 4. Since the discriminant is positive, we get two real solutions, x equals 2 and x equals 4. When the discriminant equals exactly 0, the quadratic equation has exactly one real solution, which we call a repeated root. The graph of the corresponding parabola would just touch the x-axis at a single point. For instance, if we had x squared plus 6x plus 9 equals 0, the discriminant would be 36 minus 36, which equals 0. This gives us just one solution, x equals negative 3. You might recognize that this equation can be factored as x plus 3 squared equals 0. The most intriguing case occurs when the discriminant is negative, meaning b squared is less than 4ac. Here, we enter the realm of complex numbers because we need to take the square root of a negative number. Consider the equation x squared plus 2x plus 5 equals 0. Here, the discriminant is 4 minus 20, which equals negative 16. Taking the square root of negative 16 gives us 4i, where I is the imaginary unit representing the square root of negative 1. Our solutions would be x equals negative 1 plus 2i and x equals negative 1 minus 2i, complex conjugates that don't appear on our real number line. Complex solutions always come in conjugate pairs when the coefficients a, b, and c are real numbers. This means if a plus bi is a solution, then a minus bi will also be a solution. The power of the quadratic formula is that it works for any quadratic equation. By examining the discriminant, we can quickly determine whether our solutions will be real or complex, distinct or repeated. This insight is valuable both algebraically and graphically, as it tells us how the corresponding parabola intersects with the x-axis. The quadratic formula is our key tool for solving any quadratic equation in the form ax squared plus bx plus c equals 0. This powerful formula gives us the solutions directly, regardless of whether they're real or complex. For our specific problem, we need to substitute our values. A equals 1, b equals negative 4, and c equals 8. These values come from our quadratic equation x squared minus 4x plus 8 equals 0. Let's simplify step by step. First, negative of negative 4 gives us positive 4 in the numerator. In the square root, negative 4 squared equals 16, and 4 times 1 times 8 equals 32. Our denominator simplifies to just 2. The expression under the square root is called the discriminant, denoted as b squared minus 4ac. This term is crucial because it determines the nature of our solutions. Let's calculate it explicitly for our values. Working through the discriminant calculation, we get 16 minus 32, which equals negative 16. This is a significant result because the sign of the discriminant tells us what type of solutions to expect. When the discriminant is negative, like our value of negative 16, it indicates that the parabola represented by our quadratic equation doesn't intersect the x-axis at all. Geometrically, this means there are no real solutions. Instead, we'll have complex solutions that come in conjugate pairs. Substituting our discriminant value back into our expression, we get x equals 4 plus or minus the square root of negative 16, all divided by 2. The challenge now is dealing with the square root of a negative number, which isn't defined in the real number system. The square root of negative 16 will require us to work with complex numbers, where we'll use the imaginary unit I, which is defined as the square root of negative 1. Looking at our quadratic formula, we've simplified it to x equals 4 plus or minus the square root of negative 16, all divided by 2. But now we face a challenge. How do we take the square root of a negative number? When the discriminant, that's the expression under the square root, is negative, we can't find solutions on the real number line. Instead, we need to work with complex numbers. To handle this situation, mathematicians created the imaginary unit, denoted by the letter I. The defining property of I is that I squared equals negative 1. This allows us to express the square root of any negative number. Using this definition, we can rewrite the square root of negative 16 by breaking it down. First, we express negative 16 as 16 times negative 1. Then, using the property that the square root of a product equals the product of the square roots, we get the square root of 16 multiplied by the square root of negative 1. The square root of 16 is 4, and the square root of negative 1 is defined as I. So the square root of negative 16 equals 4 times I, or simply 4i. Now we can substitute this result back into our original formula. The square root of negative 16 becomes 4i, giving us x equals 4 plus or minus 4i, all divided by 2. Let's simplify this expression further by dividing each term in the numerator by 2. When we divide 4 by 2, we get 2. Similarly, when we divide 4i by 2, we get 2i. This gives us our final form, x equals 2 plus or minus 2i. This compact form represents two different complex number solutions to our original quadratic equation. Let's explicitly write out both solutions that come from the plus-minus symbol. Remember, this notation is a shorthand for two separate solutions. Our first solution, x sub 1, is 2 plus 2i. That's the case where we use the plus sign. Our second solution, x sub 2, is 2 minus 2i. That's when we use the minus sign. Notice that these solutions are complex conjugates of each other, a pattern that always occurs with quadratic equations that have complex solutions. In summary, when a quadratic equation has a negative discriminant, the solutions involve the imaginary unit I. This extends our number system beyond the reals into the complex plane, where every quadratic equation has exactly two solutions. The solutions to our quadratic equation are x equals 2 plus 2i and x equals 2 minus 2i. These complex numbers represent the exact values that satisfy our original equation. Now we'll simplify our quadratic equation solution. We have x equals 4 plus or minus 4i, all divided by 2. This expression came from applying the quadratic formula to our equation. To simplify this expression, we'll distribute the division by 2 to each term in the numerator. This gives us 4 divided by 2 plus or minus 4i divided by 2. Calculating each fraction, we get 4 divided by 2 equals 2, and 4i divided by 2 equals 2i. So our simplified expression is x equals 2 plus or minus 2i. This is much cleaner than our original form. The plus or minus symbol actually gives us two separate solutions. Let's write them out explicitly as x sub 1 equals 2 plus 2i, and x sub 2 equals 2 minus 2i. Both of these values, when plugged back into the original quadratic equation, will make the equation true. Looking at these solutions, we can identify their parts. Both have the same real part, which is 2. The real part represents the horizontal position when we plot these numbers on the complex plane. However, their imaginary parts are opposites, plus 2i versus minus 2i. The imaginary part represents the vertical position on the complex plane. So these solutions are reflections of each other across the horizontal axis. These two solutions are known as complex conjugates of each other. This isn't a coincidence. When solving quadratic equations with real coefficients, complex solutions always appear in conjugate pairs. This is why we get two complex solutions rather than just one. Formally, if we have a complex number z equals a plus bi, its conjugate, denoted as z with a bar over it, equals a minus bi. The conjugate has the same real part but the opposite imaginary part. This property is crucial in various applications of complex numbers, from signal processing to quantum mechanics. These complex solutions tell us that our original quadratic equation has no real solutions. It doesn't intersect the x-axis when graphed. Instead, it has these two complex solutions which, while not visible on a regular coordinate plane, have important mathematical meaning. In this section, we're going to verify that the complex solutions we found actually satisfy our original quadratic equation x squared minus 4x plus 8 equals 0. Our quadratic formula gave us two solutions, x equals 2 plus 2i and x equals 2 minus 2i. These are complex numbers because they involve the imaginary unit I, which is the square root of -1. To verify these solutions, we need to substitute each one back into the original equation and check if we get a true statement. Let's start by examining our first solution, x equals 2 plus 2i. For x equals 2 plus 2i, we substitute this value into our original equation x squared minus 4x plus 8 equals 0. This gives us the expression on screen. Now we'll expand the squared term. Remember that when squaring a binomial, we use the formula a plus b squared equals a squared plus 2ab plus b squared. Here a is 2 and b is 2i, giving us 4 plus 8i plus 4i squared. Then we distribute the -4 to get -8 minus 8i. A key property of complex numbers is that I squared equals -1. This is the defining characteristic of the imaginary unit. So we replace 4i squared with 4 times -1. Simplifying this expression, we multiply 4 by -1 to get -4, while keeping the rest of the terms the same. Now we group and combine like terms. The real numbers 4, -8, and 8 add up to 0. The imaginary terms 8i and -8i also sum to 0. This simplifies to 0 equals 0, which is a true statement. This confirms that x equals 2 plus 2i is indeed a solution to our original equation. Now let's verify our second solution, x equals 2 minus 2i. We follow the exact same process, substituting this value into the original equation. Again, we expand the squared term using the binomial formula. For 2 minus 2i squared, we get 4 minus 8i plus 4i squared. Then we distribute -4 through the parentheses to get -8 plus 8i. Just as before, we substitute i squared with -1. The term 4i squared becomes 4 times -1. Multiplying 4 by -1 gives us -4. The expression now has only simple terms that we can combine. Grouping like terms, we have 4 minus 4 equals 0, -8 plus 8 equals 0, and -8i plus 8i equals 0. All terms cancel out perfectly. And once again, we get 0 equals 0, confirming that x equals 2 minus 2i is also a solution to our original equation. Now that we've verified both solutions, let's discuss some important properties of complex solutions to quadratic equations. An important property of quadratic equations with real coefficients is that complex solutions always come in conjugate pairs. If a plus bi is a solution, then a minus bi will also be a solution, just as we saw with 2 plus 2i and 2 minus 2i. Complex solutions are extremely valuable because they allow us to solve equations that have no real solutions. Our original equation, x squared minus 4x plus 8 equals 0, has a discriminant of -16, which tells us it has no real roots. Beyond pure mathematics, complex numbers and solutions have practical applications in many fields. In electrical engineering, they're used to analyze alternating current circuits. In physics, they help describe wave functions, and in signal processing, they're fundamental to understanding frequency domains. The introduction of complex numbers completes our understanding of quadratic equations. With complex solutions, every quadratic equation has exactly two solutions, maintaining the fundamental theorem of algebra. By verifying our complex solutions, we've seen how the algebraic properties of complex numbers work in practice. The ability to solve and verify these solutions is a powerful mathematical skill that extends the range of problems we can solve.